Okay guys, welcome to my tutorial. Today, the focus of this, I guess, is to go over shear force and bending moment diagrams for distributed loads. So, I'm assuming for this tutorial that you guys know how to find the reactions. I've just written that down here to find the reactions A and B. So now the first step in these problems is drawing up a free body diagram. So I'm just going to draw this up here, and I like to keep the distributed load as a distributed load rather than converting it to an equivalent point mass, because I think that makes things a bit simpler when you have to draw up the diagrams. Okay, so once I've drawn up my free body diagram, then I like to run some lines directly down from the critical points. So I like to think of the critical points as anywhere where there's a point load, and also at the beginning and the end of this distributed load. So dot all these in. I think to do these properly, it's important that you keep a good scale, so that it sort of becomes a bit more intuitive later on in the problem. You don't end up having to guess things. So give ourselves plenty of space and draw another line. So the first thing we're going to do is put in our shear force. So, and basically all you're doing is just drawing in the shear force caused by these loads. So at the start, we're going to go up 22.5. I'll write that in there. So that's the jump up there caused by the reaction at A. And then for here we have 5 meters of 5 kilonewtons per meter. So that is going to bring us down to this point here. We're going to be just below zero, because we've minus a total of 25, and then between, what's that, that's going to be minus 2.5 right there. I like to write all these in because it makes it easier when you have to later on. So then we have no change in the shear force between here and here, so that's just straight. And then at 15 we take another step down, another 15, down to minus 17.5. We'll say there, minus 17.5. Then no change until we get to the final reaction, and luckily it all matches up, and that'll bring us back to zero. It's important, if that doesn't go back to zero, then it's not really a static problem, so you've probably done something wrong. And then I just like to make my life easier by drawing them in. And that there is your shear force diagram. So the only trick there is with the 5, you've just got to think it's going to be an angle sloping down, and it's going to make a triangle shape. And that's probably the most basic distributed load, but that's all we're going to focus on at the moment. Now the bending moment is basically the area underneath this shape here. So basically it's the integration of it. So the way that what I like to do usually is you can break these up if you want into, if it's simple enough, you can break it up into areas. We'd probably separate that into 2, that into 3, and that into 4. And then you can work out what your equivalent bending moment is based on those areas. So the important thing to remember when working out the bending moment is that these areas, we're actually summing them, not adding them. So 2, 3 and 4 are going to be minused from number 1. The first step is to work out this point here. This is the point of zero shear force. This is really important for all of our questions involving shear force and bending moment diagrams, because basically all of the questions want to find the maximum bending moment, and the maximum bending moment corresponds to this point of zero shear force on the bending moment diagram. So to find that, we use a simple bit of algebra. Basically, if we're starting at 22.5 kilonewtons, this is taking away 5 kilonewtons per meter. So we're going to end up with 22.5 minus 5x equals to 0, and then we can sum our x at 4.5 meters, and then we know that point, that x value on the bar, on the beam, or whatever it is. And so from there, once we have that, we'll come to more of that later, but now we can work out all of our areas. So one is simply area of a triangle, half times the base times the height, half 4.5, and you've got them all there. I'll save you the calculations, it's not particularly exciting, just the areas of triangles and rectangles. And it's important to get the negatives right, because that can be a problem later. So once we've done that, it's time to draw our bending moment diagram. So as I said before, it is the integration of this line. So basically, if you think of this line is minus 5x. So if you've got, say, the 5 isn't particularly important here, but basically if you have minus x and you're going to integrate that, the integration of minus x becomes minus x squared on 2. So you know it's going to be an upside down parabola for that portion of this. So we can draw that in now as something like that, and you're going to know that the peak is going to correspond to that 0 value there, and then because that's the maximum bending moment, as I said, so the maximum is always going to be at that 0 value. So that's a sort of rough upside down parabola, but you get the idea. And then from here, it's pretty simply, this is minus 2.5, and these are constant, so they're going to be, rectangles are going to be straight lines, and this is going to have a gradient of minus 2.5, and then there, and then once it gets to the 17.5, it's going to be steeper. We're going to come down to there like that, and then you can do the same thing and draw your lines in. So what should end up happening is your bending moment should basically look like the inverse of how your beam will bend. So if you got this and flipped it over, you'd see you'd have the curve going down here, then your straight line, and then your other straight line. So that's just like, for me, it makes sense. It's a quick way of making sure that you're sort of on the right track with your bending moment diagram. So the last thing that we'll probably do in this is your maximum bending moment, which is at that point there. It's always good to write it into your diagram, and it's simply this. Since it's the integration of this, it is going to be the area under here. So that we already calculated that at 50.625 kilonewtons, and that corresponds to our maximum bending moment on this beam. And that's all I'm going to cover in this. Thank you very much.